Okay, I'm going to get back to section 11.5 here. We're talking about operations with functions. So far we've looked at just the basic four operations: add, subtract, multiply, and divide. There is another operation that we need to be familiar with that is pretty important, and that's called function composition. So here's a definition. Let f and g be functions, then the composite function, which is denoted by f composed g, is how we'd read this. And we define this as f composed g of x equals f of g of x. Okay, with function composition, you're plugging one function into another function. Whatever function is written after the open circle, you're going to be plugging that one into the one that's before the open circle. Okay, so basically how this is written, you're going to be plugging g into f, not f into g. Let's take a look at problem 34. We have f of x is x squared minus 3x and g of x is 2x plus 1. Okay, part A, we're going to compute f composed g of x. Well, by definition, that means I need to plug g into f. G is 2x plus 1. Okay, so everywhere that I see an x in f, there's two of them, I need to replace those with 2x plus 1. And so I've done that on the next line. Now I would just simplify. So 2x plus 1 squared, that's the same as 2x plus 1 times 2x plus 1. When you FOIL that out, you would get 4x squared plus 4x plus 1. Minus 3, I'll go ahead and distribute the negative 3 there into the two terms and be a minus 6x minus 3 then. Collect your like terms. You got 4x squared, 4x minus 6x is minus 2x, and then 1 minus 3 is negative 2. Okay, and 4x squared minus 2x minus 2 would be my answer then. That'd be called the composite function. Like any other function, we have input values and output values. So like if I wanted to find f composed g of 3, I could handle the calculation like I did when it was x. Okay, I need to find f of g of 3. G of 3 is 7. So essentially in this problem, we're just asked to find f of 7. Okay, well here's f of x, plug in 7. 7 squared is 49, minus 21 is 28. I could also compute f composed g of 3 by just plugging 3 into this formula that I built, right? I've already built it in terms of x, so I can let x be anything I want here. If x is 3, okay, 3 squared is 9. Times 4 is 36, minus 6 is 30, minus 2 is 28. Like I'd still get 28 there. Okay, now we need to not get this confused with another operation that we've already talked about, which is the product function. Students will sometimes do that. They see this open circle here, and for whatever strange reason, they think multiply. Don't do that. Okay, the composite function and the product function are different functions. So like in part C, just to show you these are different, I'm going to go ahead and compute the product function. F of x times g of x means I just multiply these two expressions. I'd have to FOIL it out here. So x squared times 2x, that's 2x cubed. The outer terms, that'd be, and the inner terms, I'd be adding x squared minus 6x is a minus 5x squared. And then negative 3x times 1 is a minus 3x at the end. Now notice how this result is not the same as this result. Okay, two totally different things. So don't make that mistake, by multiplying when you're asked to find the composite function there. All right, and there's the caution statement that I've pretty much already summarized there. Part D. Okay, g composed f of x. Well, here I've switched the functions. So basically, where I see g, I'll write f. Where I see f, I'll write g. Okay, this means that I'll be plugging f into g. So now f of x is x squared minus 3x. Everywhere that I see an x in g, there's only one. Replace that with x squared minus 3x. And then simplify. You'll need to distribute 2. And we end up getting 2x squared minus 6x plus 1. Notice that these two results here are different. G composed F is not the same as F composed G. Now, sometimes these will be the same. It didn't happen here, but sometimes they will actually be the same. And when that happens, it's special because we say that F and G are inverses of each other. We're going to look at the topic of inverse functions in the next section, actually. When we calculate a composite function, we are taking the output values from one function and using them as the input values for another function. There are lots and lots of applications of the composite function. Converting units is the application, in my opinion, of function composition. Okay, for example, suppose that we wanted to know how many inches are in a mile. Many people wouldn't know that off the top of their head. Okay, but this is just a simple calculation involving function composition. If we knew how many inches were in a foot and how many feet are in a mile, then we could very easily find out how many inches are in a mile. That is function composition. Okay, so let's take a look at problem 35 here. There are 5,280 feet in 1 mile and 12 inches in 1 foot. Okay, part A. Write a function f of x that converts x inches to feet. Well, if I know that there's 12 inches in 1 foot, x over 12 would be just a general formula that converts x inches into feet. So like if x is 12, 12 over 12 is 1, 12 inches would be 1 foot then. If x is 24, 24 over 12 is 2, so there's 24 inches in 2 feet. If x is 6, 6 over 12 is 1/2. Okay, there's 6 inches and 1/2 of a foot, etc. Part B. Write a function g of x that converts x feet to miles. Well, they told us that there's 5,280 feet in 1 mile. So the formula that we would be working with here that converts feet to miles would be x over 5,280. In other words, if x is 5,280, 5,280 over 5,280, that'd be 1. Okay, so there's 5,280 feet in 1 mile. Now, in part C, we want to compute f composed g of x and then simplify. This is going to be the function that allows us to convert x inches to miles, okay, which is what I was describing up here. Okay, well, like what if somebody wanted to know that? Well, f composed g of x means that I need to plug g into f. Okay, here's f of x, here's g of x. G of x is x over 5,280. So everywhere that I see an x and f, there's only one. Replace that with x over 5,280. And so I've done that. Okay, now you're dividing by 12. Think of 12 as 12 over 1. And when I flip the denominator and multiply, x over 5,280 times 1 over 12 would give me x over 63,360. Okay, and that would be my answer. That would be the function that allows me to convert x inches to miles. All right, now in part D, let's compute f composed g of 15,840. Okay, well, I can plug that number into the formula that I've created here. 15,840 times 4 would give you 63,360 if you were to check that. So I would get 1/4 then as my resulting number when I simplify. Okay, interpret this result. X was 15,840 inches. Okay, and I've produced a formula that allows me to convert x inches to miles. So in other words, if you had 15,840 inches, that would be 1/4 of a mile. If I had 63,360 inches, okay, that would be 1 mile then, right? And if I had x inches, I could know from this formula how much of a mile that is. Notice how this is function composition here. Okay, it's just an application. Try problem 36 is another similar application. Suppose that we wanted to know how many cups are in a gallon. Unless you bake often, you might not know that. Okay, so there are 4 quarts in a gallon and 4 cups in a quart. Part A, write a function f of x that converts x cups to quarts. Okay, well there's 4 cups in 1 quart, they told us. So the formula that I would have here is x over 4. Okay, if I had 4 cups, 4 over 4 is 1, there'd be 4 cups in 1 quart. Okay, or if I had 2 cups, that would be a half of a quart. Okay, 8 cups would be 2 quarts, etc. Part B, write a function g of x that converts x quarts to gallons. Well, I was told that there are 4 quarts in 1 gallon. So x over 4 would be the formula that allows me to convert x quarts to gallons. Okay, if I had x is 4, let's say, 4 over 4 is 1, okay, so there'd be 4 quarts in 1 gallon. If x is 8, there'd be 8 over 4 is 2, so there'd be 8 quarts in 2 gallons, okay, etc. Part C, compute f composed g of x and simplify. Okay, so that means that I need to plug g into f. And here's g of x, it's x over 4. I'm going to plug that into f, where I see x. X over 4 divided by 4. 4 is the same as 4 over 1. Okay, so I'm going to flip the denominator and multiply. X over 4 times 1 over 4 would be x over 16. This is the function that allows us to convert x cups to gallons. Okay, so like if I had 16 cups, 16 over 16 is 1. 16 cups would be in 1 gallon. And that's the thing here, the question that I want to know. What if somebody wanted to know how many cups are in 1 gallon? Well, it'd be 16. Okay. Part D, compute f composed g of 32 and interpret this result. Well, if x is 32, 32 over 16 is 2, and we would interpret that as there are 32 cups in 2 gallons. Okay, and I could know how many cups are in a gallon from this formula, if I had x cups, I could know how many gallons that is. Again, just an application of function composition there. Okay, problem 37 is another application. So scientists often have to work with temperatures and the common unit measurements that they would work with would be degrees Fahrenheit, degrees Celsius, and kelvins. Okay, so suppose that you had a temperature that was in kelvins or in degrees Fahrenheit, excuse me, and you wanted to know what that would be in kelvins. Okay, well you'd have to know unit conversions. Okay, there's a formula that allows you to convert a temperature in degrees Fahrenheit to Celsius, and then there's another formula that allows you to convert a temperature in degrees Celsius to kelvins. It says the function c of f converts a temperature in degrees Fahrenheit to a temperature in degrees Celsius. The function k of c converts a temperature in degrees Celsius to a temperature in kelvins. Part A, find a function that converts a temperature in degrees Fahrenheit to a temperature in kelvins. Well, I would just work with function composition here. K is a function of degrees Celsius, and the degrees Celsius function is a function of degrees Fahrenheit. So I would just simply plug c into f. C is already a function of degrees Fahrenheit, right? So we need to find k of c of f, or k composed c of f means the same thing. Here's C of F. Okay, so everywhere that I see a C in K, there's only one of them, I'm going to replace that with this expression here. And so that's what I've done. Okay, replaced C with 5/9 times F minus 32, and circle this result. Okay, so this would be just a general formula that allows you to convert a temperature that is in degrees Fahrenheit to a temperature in kelvins. What if we wanted to know what 95 degrees Fahrenheit is in kelvins? Well, I can figure that out now, right? I've got a formula that allows me to do that. F is 95 degrees. Plug that into the function here. 95 minus 32 is 63. 63 divided by 9 is 7. 7 times 5 is 35. And I've got to add 273 to 35. That'll get me 308 kelvins. Okay, so 95 degrees Fahrenheit is the same as 308 kelvins then. Okay. Let's stop the video here.